Alright, so today I'm going to be explaining this paper in NeurIPS 2024. Previous video was about ICML 2024. Today I want to talk about NeurIPS 2024. And both of these two papers are about constraining. For example, previous video we use optimization, that KKT condition, in order to iteratively project your graph into a valid space graphs, and then do so each iteratively in denoising process. We first project and then denoise. But this paper, it has a slightly different approach, but the idea is very similar. So graph diffusion models have emerged as state-of-the-art techniques in graph generation. Yet integrating domain knowledge into these models remains challenging. Domain knowledge is particularly important in real-world scenarios where invalid generated graphs hinder deployment in practical applications. Unconstrained and conditioned graph diffusion models fail to guarantee such domain-specific structural properties. So they present this construct model, which is a novel framework that enables graph diffusion models to incorporate hard constraints like number of triangles in a graph that we discussed previous video, such as planarity, acyclicity, number of for example, single bonds. Our approach ensures that the sample graphs remain within the domain of graphs that satisfy the specified property throughout the entire trajectory in both the forward and reverse process. This is achieved by introducing edge-absorbing noise model and a new projector operator. Oh, by the way, when we usually in discrete domain, when we talk about this forward transition, the three main ideas come to your mind. First is just the uniform transition. So your matrix of Q has a particular form that has uniformly distributed among K classes, or you can have what we call absorbing, that it absorbs to some state, for example, a mask state. And a mask state never comes to a category. It stays in mask forever. If it is mask, it stays forever. The third one is the Gaussian, which is the Gaussian. You use the Gaussian in the continuous domain to the discrete space. It's interesting. But here, this Gaussian, we look at it, is similar in that when you go from state I to J, what happens to the transition kernel? The forward transition. And this is the constrained graph discrete diffusion framework. The forward process consists of an edge deletion process driven by edge absorbing noise, while node types may switch according to the marginal noise model. Do you know why we say all these absorption here in this context? Because absorption, generally, even in dynamical system, you have absorbing subspace. Your trajectory of dynamical systems, after a while, it goes in a particular area of your subspace and remains there forever. So it becomes an invariant subspace. The same idea, this was for dynamical system over a manifold. The same idea here on graph is the same. After a while, you reach some particular state space of your graph, which is, because it's our state space, it's just nodes, node types, and edge types. At least for this example of 2D graph generation. And so these are notation as usual. We have stack tensors, X and E. The importance is we consider the absence of edge between two nodes as a no edge type. we have seen this in many papers. No edge type, they added as a kind of type to make it more dynamic. But this is just one of the approaches, not all approaches. You can use a different approach. These are stacked in tensor and so equivalently to the set notation. We define this probability simplex here, that the sum of all of them is equal to 1. So they define here what is edge deletion invariance. Let P be a Boolean valued application defined on graphs referred to as a property. P is said to be edge deletion invariant if for any graph G and any subset of edges, it satisfies that if P of G is true, P of G prime is true with G prime to be XE exclude E tilde. So many properties that are observed in real-world scenarios are edge deletion invariant. For example, graph planarity is observed in road networks, chip design, biochemistry, digital pathology. So the forward for the edge deletion aware forward process looks like this. So look at the transition matrices for both the nodes and for edges. And M prime and E prime are row vectors filled with marginal node distribution and one hot encoding of the no edge state. So this is an edge absorbing noise model. This noise model forces each edge to either remain in the same state or transition toward an absorbing state, which we define to be a no edge state. So sometimes your absorbing state is masked, but in this paper, your absorbing state clearly said that it's a no edge. For example, between these two nodes, there is no edge. So we call it no edge. And when it goes to that state, it remains there forever. So when you delete an edge, it remains there forever. You don't do it again. You don't create it again and then delete again. You don't do this. The reverse process is fully characterized by P theta of this. So we refer to the operator that outputs GT minus 1, provided GT minus 1, and by discarding the violating edges as the projector. Those, for example, you have a validity constraint. If those new edges are violating, then we just discard these violating edges using this module called projector. So the theorem is interesting that G star can be recovered by our projector. The training is very simple. The denoising network, if you look at their appendix, they just use a cross entropy loss between predicted probabilities for each node and edge type. So similar to digress, if you remember. In digress, you don't need any Gumbel softmax because the output is just the logits and everything is continuous, no problem. But if your forward needs to be trainable, then you definitely need the Gumbel softmax because the sampling process is is really not a continuous thing that PyTorch geometric can backpropagate through that. So you need a Gumbel softmax. But if your forward is okay, I mean it's fixed, you don't need to train it, then you just for the training you don't need any Gumbel softmax. Everything is continuous differentiable. And so here is the training algorithm for graph discrete diffusion. So simple. So just like digress, they add extra features for sampling. But here, look at this. We insert only valid edges. And the sampling, the only difference is that now we do projection before going to the next step of denoising. Just like previous video that we talked, it was the same thing. We had a projector, and so their constraint, like previous video, could be anything.